Hello. We are now ready to continue the discussion of timbre, which, as you recall, is a qualitative aspect of sound. It's kind of the thing that makes a trumpet concert A different from a violin concert A, which is different from drums, right? So even if the pitch is the same, and even if the loudness is the same, there's something that's qualitatively different about those things. What's interesting is the qualitative difference often boils down to a difference in harmonics. So all these things that come out of physical processes, they resonate at a particular frequency, and they also resonate at integer multiples of that frequency. But not all the integer multiples are going to be equally powerful for all the different kinds of instruments, and some of them may even be missing. And that is in large part what makes the sounds have their unique quality. So where this is going to end up by the end of the module is we're going to see how to make a variety of instruments. I mean, we've talked a little bit about pluck strings so far, but we're going to go beyond that. We're going to talk about brass sounds and percussive sounds. And we're going to see that actually we can do them all in the same pretty simple framework called FM synthesis. It's kind of surprising how general this one idea is. So we'll get to that in a moment. But I do want to go over the exercises from today. Even though most people got them, I want to go over them and make my own observations and kind of talk about what people tend to think about these different examples in music applications. So in every example, I was adding together a bunch of sines and cosines to make something, and they were all harmonics of each other. So, I could start off just by saying, all right, so I'll make a sample rate of 44,100 samples per second. I'll say that my times are, maybe I'll make 2 seconds worth. And, I could say, all right, well, let's make the bass frequency concert A we like. And, I could just add all the harmonics equally. So I'll add the bass frequency and harmonics. I'll say 4i in range 111. So maybe I'll go from the bass frequency at a ratio of 1, and then up to 2, up to 3, up to 10. So the bass frequency in its first 9 harmonics. So I could say this, 2 pi times the frequency 0, but actually, we're going to scale the frequency by that integer times the time. So I'm going to add this on. I'm going to add all these sinusoids on. Okay, so what I'm going to do is I'm actually going to just plot the beginning of this. Now I told you to plot the first 300 samples, but here's another thing you could do. If I plot the waveform versus time, I could then say PLT to zoom in on just a little bit. I could say let's zoom in on the first maybe 50 milliseconds or something. Okay, so I can set the X limit on the X-axis there. So let's see how this goes. And actually, you know what? I think I want to zoom in even more. Okay. So in the first 10 milliseconds. So here's what the waveform looks like, and let's hear it. Okay, what happens is I add more harmonics. So let's go up 10 more. So you see it gets a little sharper, right? These peaks get higher relative to what's around them. And the sound gets a little grittier, right? So we can still hear the same note. We still hear that this is a concert A. But we hear a little bit more of that almost like gravelly sound. And if I add even more, you see it happening even more. And if I dial back, by contrast, if I dial back to just 5 harmonics, you see, it doesn't wiggle quite as much. It still has the little wiggles, but it doesn't sound, it sounds a lot smoother in a way. Okay. But this is just one of many ways that we could choose to add the harmonics. I mean, one of the things that's a little unusual about this from a physical point of view is that all the harmonics are in equal frequency or are in equal amplitude the whole time. But as I explained, one thing you can do is put them in what's called a harmonic sequence, amplitude sequence. So what I can do is I can actually decrease the amplitudes just at a linear fall off in the harmonic number. So the bass frequency doesn't change when I is 1, but then the first harmonic when I is 2, I divide that amplitude by 2. For the next harmonic, I divide it by 3 and 4 and so on and so forth. And also I'm going to change this from a cosine to a sine. So let me do that. And here's what I get. So already this is looking a little bit familiar in some ways. Okay, so this is what's known as a sawtooth wave. We actually saw this. This is the first thing that we ever looked at in the course. We did it a different way. We did it by saying, well, let's, I'll call y2. That's going to be equal to mp.a range SR times 2. And then remember we took the modulus. So we said we could do A range, which is just a single ramp. It's just going to increase, increase, increase. But if we do the modulus by 100, as soon as it gets to be a multiple of 100, it jumps back to 0 again. So I can plot this as well. And what I'll see is the following. So it looks like this. Now, okay, fine. These are basically negatives of each other. So let me just go ahead and instead of saying plus equals sine up here, I'll do minus equals to be consistent. Okay, now these are quite similar in shape. So let's listen to the difference. So there's my 5 sinusoid version, and here's my modulus version. Well, they don't sound that different because this one's actually y2. Hang on. Okay, here's the sinusoid version again. Okay, so hear how much grittier this one sounds? So the way that you can see this is if I add more harmonics, this one's going to start to sound more like this one. So let me go up to 20 frequencies total. So see it already, you can see it already looks a little more like that, right? It's able to get these sharper transitions. You still see some of the wiggles left over. It's not totally straight like this one. But let's listen. I mean, that's a lot closer than it was. You know, if I dial back to just 10, you'll hear a difference. So anyway, I like to think this really to me is more of, I mean, these are all called sawtooth waves. This one actually looks like a sawtooth, right? Okay. But so one of the things people say is this is almost like modeling a cheap version of a bowed string, because as the bow goes across the string catches the bow and then slips. So it catches, goes along with the bow, then slips down, catches, goes along, then slips down. Let's listen and see. Does this even sound like a bowstring? Maybe. Maybe we convince ourselves, I don't know. But anyway, it's definitely got a unique timbre, and you know, it's determined by these ratios here. Okay. So that's cool. And the other takeaway, which we'll talk more about, certainly next week and the week after, is that you can approximate this shape by summing together sines and cosines that are all in integer ratios of base frequencies. So that's pretty interesting. Okay. Now let's look at another example. So I said do kind of the same thing, except only do it for the odd harmonics. So I'm going to skip, all the even ratios. And I'm also going to flip the sign every time I do this. So, if base frequency is positive, but then 2 later it's negative, 2 later it's positive again. So kind of the same code. But I'm going to say if I mod 2 is 1. So this will take only the odd harmonics here, or only the odd ratios is what it's doing. So we got that, and then also I need to I'll go back to doing plus, but I need to flip this sign every time. So I'll have a little variable called a, which starts off at 1, and every time I add on a new frequency, I'll negate it so it goes in that ratio. Okay. So let's look. And I think I also, let's see. I think I also want to change this to a cosine. Is that right? Yes. Okay. All right. So maybe I forgot to mention that in the exercise. But anyway, okay, so here's the shape. So let's listen. Okay. Dial it back a little bit. You see, it's a little smoother. And you can hear it too, right? And of course, if I dial all the way back to a pure tone, you get the most boring sound possible. Okay. So the more harmonics I add, the more it kind of gets some color. All right. Now, how does this sound compared to the Sawtooth? Let's just listen. Okay, so they're a little different. People in class, well, I'd done something like this, said it sounded like a video game tune. And there's a reason for that. So this is looking a lot like something else we saw. This is looking like the square wave, right? So if I say y is equal to mp dot cosine 2 pi ft, and then I put the sign function around that. Remember, that's going to, everything that's below 0 is just going to clamp to -1. Everything that's above 0 is going to put a 1. If I do that, and I look at the result, then what I'm going to see is this. And you can see how similar these shapes are, right? You can see they're at the same period. And they're basically doing the same thing. This is just a wigglier version of it. So if I play both of these, I can hear the same sort of thing where this one it's grittier, right? And the reason okay, so this was used in video games. Well, this is pretty easy to make in hardware because it's basically like binary. You're either at a 1 or you're at a 0. So you kind of need one bit to describe this, right? So very cheap to manufacture. But just like with the Sawtooth Wave, if I add more harmonics, I get something that's closer and closer to looking like this. And I can hardly hear the difference once I add enough harmonics. Okay. Cool. So let's just do one last example, right? So this one says, I also want to add all the odd powers, alternating positive and negative frequencies. So basically the same thing, except I want to not divide by I, but actually divide by I squared. So the harmonics, the higher harmonics are going to be weaker in this one. Let me see. Okay, there we go. Yeah, let me just go back down to 5 frequencies. Okay, so this one's interesting. I don't think we actually made this one before, but you can see that this one is what's called a triangle wave. So if I only have a few, it almost looks like a sine wave. But if I add more, it starts to get pointier at the top. So let's just listen to them all together. And you can definitely hear between the square wave and the triangle wave that the triangle wave is a little bit sort of dampened, right? You don't hear those high harmonics as much. So it doesn't sound quite as gritty because we're falling off with the harmonic number squared, not just the harmonic number. So by the way, people tend to think that this maybe is like a clarinet. Because the air kind of comes out of a vibrating tube in this way. But anyway, these are all very cheap approximations. But you'll hear these because they're easy to make. You'll hear these primitive sounds, right? Like I told you, and especially in cheaper hardware. So anyway, I just wanted to go through those examples. But now we're going to build up some more.